In this video, we continue our discussion about continuous and discrete probabilities. We discuss ways to describe the probability of an event. Depending on whether the target space is discrete or continuous, the way we refer to distributions is different. When the target space T is discrete, we can specify the probability that a random variable x takes a particular value x in the target space. We denote this by the probability that capital X equals little x. The expression P of capital X equals x for a discrete random variable x is known as the probability mass function. Target space T is continuous, that is, functioned on a real line. It's more natural to specify the probability that a random variable x is in an interval. By convention, we specify the probability that a random variable x is less than a particular value little x, and we denote this by probability that x less or equal to little x. The expression, the probability that capital X less or equal to little x, for a continuous random variable x is known as a cumulative distribution function. We use the phrase univariate distribution to refer to distributions of a single random variable whose states are denoted by non-bolded x. Distributions of more than one random variable as multivariate distributions, and we'll usually consider a vector of random variables whose states are denoted by a bold-faced x. When the target space is discrete, we can imagine the probability distribution of multiple random variables as filling out a multidimensional array of numbers. The target space of the joint probability is the Cartesian product of the target spaces with each of the random variables. We define the joint probability as the entry of both values jointly, the probability that x equals xi and y equals yj. And of course, this is equal to nij in the diagram divided by capital N, where nij is the number of events with states xi and yj, and n is the total number of events. The joint probability is the probability of the intersection of both events. That is, the probability that x equals xi and y equals yj is really the probability that x equals xi intersect y equals yj. For two random variables x and y, the probability that x equals x and y equals y will lazily be written as the probability of x and y and is called the joint probability. One can think of a probability as a function that takes state x and y and returns a real number. And that's why we have this convention where we write the probability as if it were a function. The marginal probability that x takes the value of little x, irrespective of the value of y, is lazily written as P of x. We can see here that the probability that capital X equals little x is equal to Cij, so that the sum of all the entries in that column divided by n. We write this lazily as P of x. Similarly, if we want to look at the probability that capital Y equals little I, we look at row J and divide the sum of the entries there by n. We write x tilde P of x to denote that the random variable x is distributed according to P of x. If we consider only instances where capital X equals little x, then the fraction of instances, the conditional probability, for which y equals y will lazily be written as the probability of y given x. Consider only instances where capital Y equals little y, then the fraction of instances for which capital X is equal to x is written lazily as P of x given y. See here that the probability that x equals xi given y equals yj is nij divided by the sum of the entries in row j. Similarly, if we look at the probability that y equals yj given x equals xi, that's equal to nij divided by ci. That's written lazily as the probability of y given x. Machine learning, we use discrete probability distributions to model categorical variables. For example, we could use the number of cars owned by an individual as a way of predicting the salary of that person. The next section will discuss continuous probabilities in more detail.